All right, so section 2.6 deals with related rates. Your essential questions are, what's your process to solve related rates? Describe. So once you go through and you're working out the problems, you kind of figure out a system that works for you, write that down. What is your process to solve related rates? And then optional, as you're going through that, are there any formulas that keep coming up? So formulas to remember. And this would just be if you're finding that something keeps coming up and up and up and you're struggling to remember, you might want to put that down here so that in your summary, your attention is drawn to that. Your objectives are just that you have to be able to solve related rates, application problems, and so let's start to take a look at what we mean by a related rate. Related rates, we're looking at how two or more related variables, so just in the same equation basically, are changing, but changing with respect to time. When we go to take derivatives then, usually we're using implicit differentiation because it's with respect to time, and most often our formula doesn't involve time in it. So that's how it ties into implicit differentiation from 2.5. In order to make these work, we have to have a good understanding of what constant variables will be in our problems versus changing variables in our problems. So we'll look through some situations here and try to decide what is constant and what is changing. A cylinder filling up with sand. If you're going to fill a cylinder up with sand, that's a volume idea, so filling up. And so just basic understanding of volume in case you have to generate a formula on your own. It's just the area of the base of whatever you're talking about times the height. So in our example, this is a circle. We have a circle for a base, top and bottom. So the area of the base piece, actually let me switch. The base part is a circle. Our area then will be pi r squared for that. So our volume formula will be pi r squared h. In that situation, if you are filling this up, so your sand level will rise and rise and rise as you're filling it up. As that happens, you need to decide, do you think the radius is constant or changing every time? Do you think the height is constant or changing? Well, if you're filling it up, the height is changing. Sometimes it's going to be really low. As you move to the top, it's going to be taller and taller. But the radius, since it's a circle on the bottom and on the top, this circle is the exact same as this circle as far as size. Radius is always the same here, or always constant here. Doesn't matter how much sand is in our cylinder, the radius at all the different levels would be the same. Next example is talking about a ladder sliding down a wall. And so if we kind of label what's going on, here's our ladder, and it's sliding down this wall. As it's sliding down, the part making contact with the ground is going to be sliding out. And then if we put some letters with this problem, I usually go back to like coordinates, how we would graph points and lines and such. So I would put X for the bottom and I would put Y for that height and then maybe Z for the ladder. You could do L for the ladder if you wanted. So as we're talking about variables in this situation, usually they will tell you that your building is making a right angle with the ground, and so the equation we'll work with quite often will be x squared plus y squared equals z squared to look at the different sides using Pythagorean theorem for those lengths. As we look through at x, y, and z, try to figure out what you think is changing and what you think is always the same. Well, this ladder that I have, yes, it's moving, but it's the same size ladder all the time. So Z is just the ladder length, and it's constant. It's not changing at all. But as the ladder slides down the wall, then Y is going to get shorter and shorter, and X at the same time is going to get longer and longer. So these are both changing. And if we talked about the X part would be lengthening as it's sliding out. And then the Y part would be shortening because as it's sliding down, you have less and less height there. So in terms of derivatives, we will look at like dx dt, the rate of change of x with respect to time. Dx dt would be positive because x is getting bigger and bigger. But dy dt, the rate of change of y with respect to time, is going to be negative because y is getting shorter and shorter. And last one we're going to take a look at before we actually work with problems, if you have an inverted conical tank filling up with water. So again, the whole filling up idea, this is a volume idea. Volume for a cone is pi over 3 r squared h. You would actually be given that formula. You won't have to know it. But we want to think about between the r squared and the h, as I have more and more water going up my cone, are any of those constant or are they changing all the time? Well, we had, our first example was a cylinder where I had a circle on the top and I also had a circle on the bottom that was exactly the same. But in this particular example, the circle that's on the top and the circle that's going to be forming all the way up as the water level changes, they're not the same. You have little bitty circles at the bottom and they get larger and larger and larger. So in this case, both R and H change. It's not the same circle on the bottom that it is at the very top. And so you would have smaller and smaller values for R and H at the bottom, larger and larger as you progress to the top. Okay, I'm going to pause and just make sure that that recorded okay.